now we want to find the formula for the sum of the first n positive integers. Now, of course, we had solved this before. We had showed that this is equal to n plus 1 over 2 by induction. But we said, again, the issue with induction is that generally you need to have a way of guessing the formula and so on. Now we're going to show how you can solve this type of problem by using the tools that we have with recursion. So it's not going to involve any type of guessing. You will just use the technique and we will solve it. So the first point is we need to convert this into some recursion. And so the idea is that you can actually write this. So note that an, right, you can write it like this, and that this first part here is essentially an minus 1, which means that an is equal to an minus 1 plus n, right, with initial condition a1 equal to 1. So this is our recursion. It's not homogeneous because of this n term. And so now let's find the general solution for this. And so the first step was solving the homogeneous case, which is when you ignore this n part. So let's do that. So if the homogeneous version, we don't have that n part, so we're just solving this here. Now this is a very simple recursion. You can just look at it. If an is equal to an minus 1, it's just the same value. So this is just going to have a constant solution. But let's write this out in the way that we were doing before. So let's solve it and confirm that it makes sense with the intuition. So the first step is writing out the characteristic equation. So the characteristic equation for this is going to be r minus 1 equal to 0, and this implies that it has the solution, so r equal to 1. And so since the solution is r equal to 1, and with one distinct root, so there's no way to have one repeated root, so in this case one distinct root, because you can have at most one root, then the solution to this, the general solution, is given by an equal to some constant times 1 to the power of n. This is the r to the power of n, but 1 to the power of n is always 1, so this is just a constant. Which again, we're just saying that the recursion is the next value is equal to the previous one, so it's always going to be just a constant, and so this is alpha. Now the next step is we need to find a particular solution to our problem. So we need to find a particular solution to this recurrence here. So first we need to identify the homogeneous part. So the homogeneous part, f of n, is going to be equal to n in this case, which you can just write it as 1 times n plus 0 times 1 to the power of n. So again, here I'm writing it out in the way that we can use our theorem. So we had our general theorem for this. So again, when we have particular solutions, if our f of n can be written as a polynomial times s to some power of n, we have these two cases to look at, and we can do that. So in this case here, our f of n is a polynomial in n times 1 to the power of n, so this is our s. So in this case, since s equal to 1 is a root with multiplicity 1, so multiplicity 1, then by the theorem, so if we go back to the theorem here, so s is a root with multiplicity 1 here, so we're going to have this expression here. It's going to be n to the power of 1 times a polynomial here times 1 to the power of n here. So in other words, if we just write that here, we have the following form. So the particular the particular solution is going to be of the form n times p1n plus p0, 1 to the power of n. Of course, 1 to the power of n is just 1, and so if you write this out, this is just going to be p1 n squared plus p0 times n. And if we substitute this now in the recurrence here, this particular solution, what we get is going to be p1 n squared plus p0 n. So that's this part over here, an. And this will be equal to an minus 1 plus n, right? So an minus 1, that's going to be p1 n minus 1 squared plus p0 n minus 1 plus n. And now we need to expand this to find the coefficients. So let's do that. So this is what we're looking at. We have this equation here. And the way that we do this is we essentially equate the coefficients. So the p1 of the p1 here, we can equate the coefficients, and what we get is the following, that we need to essentially solve minus 2 p1 plus 1 equal to 0, and p1 minus p0 equal to 0. So solving these, we obtain p1 equal to half and p0 equal to half. And thus the general solution, is going to be an equal to the homogeneous solution plus the particular solution. And so this is going to be, the homogeneous solution was just the constant alpha. And now for the particular solution, it's going to be half n squared plus half n. And now we use the initial condition, alpha 1 equal to 1 to solve for alpha. Now, if you replace that, so alpha 1 equal to, sorry, not alpha 1 equal to 1, a1 equal to 1 to solve for alpha. So when you replace a1, you're going to get, so we know that a1 is equal to 1, so you're going to get 1 equal to alpha plus half times 1 squared plus half times 1 here. And this implies in alpha equal to 0. Thus, the final solution we get is an is just going to be n squared over 2 plus n over 2, which you can rewrite it as n plus 1 over 2, which is what we had seen before when we proved by induction, but here we showed how you can solve it using the tools that we learned for solving recurrences.